Swayam Prabha. Digital India. Educated India.
Hello everybody. Today we will be discussing a very important ultra high vacuum pump which is called Cryopump. In fact, Cryopump is the ultimate. Where every pump fails, Cryopump will start working there, because enormous pumping speeds and extremely low temperatures and pumping mechanisms are totally new compared to or unconventional rather compared to other pumps, and it is a most modern technology is involved like cryogenic engineering. Okay. And this cryo word is also very important, because in deep space we have a lot of cryogenic conditions, and in deep space we also have vacuum conditions. That way 99.999% of the universe is under vacuum conditions, and once you go into the deep space, excessively cold temperatures are there. Only on earth we have the living conditions like 25 degree, 30 degree, nowadays it is 40, 50 degrees, but otherwise towards sun it is very hot side, but other side it is going to be very cold. So, cryogenics and vacuum, these are recently last 100 years they have developed, but they are naturally available in nature, and we are only trying to couple these cryogenics and vacuum in cryopump. Normally, vacuum pump is required to produce a thermally insulated atmosphere, so that cryogenic conditions can be established. That is how vacuum technology helps cryogenic engineering. But in this cryopump, it is reverse. Cryogenic technology helps vacuum technology. But of course, initially to produce cryogenic temperatures, you require thermal insulation, and under that convection can be reduced only under vacuum conditions. So, first vacuum, with that help we produce cryogenics, and with those cryogenic conditions we produce vacuum again, which cannot be produced by any other pump. So, cryopump has got a lot of history behind it, and lot of stages are there in the developmental activity, and today very high quality cryopumps are being manufactured, and which are regularly being used in semiconductor industries and space technology, nuclear technology, like that. Okay. In this course, we will be covering introduction of the cryopumping, construction of a typical cryopump. There are varieties of cryopumps I will show, but typical pump. Then we will also see the operating principles behind cryopumping. Towards the end, we will see some applications, strategies and advantages, and finally some limitations. Okay. What is cryopumping? So far in the earlier pumps, we have seen positive displacement pumps like rotary, turbomolecular pump, etc. We have also seen in between one adsorption pump or gettering pump, where the molecules are not taken out of the chamber, they are trapped by surfaces. If it is a physical adsorption, it is physisorption pump. If it is chemical absorption, they are called gettering pumps and all. So, already we know the surface pumping phenomena earlier, but in cryopumps, they are the only processes used where there is a condenser inside your vacuum chamber, which is cooled to cryogenic temperatures. Cryogenic temperatures means minus 196 degrees liquid nitrogen, again minus 269 degrees with liquid helium. These technologies are well established. We have a cryogenic engineering center at IIT Kharagpur. Similar centers are there in all other IITs also, some part of the department, etc. So, cryogenic engineering is very well established Cryogenic rocket engines, most of you must have heard in India, and they are the last stage which has got huge thrust to lift our satellites into geostationary, etc. Anyway, I am not going to cryogenics, which is my main area, but in cryopumping we will have cryogenic condensers, and those condensing surfaces are pumps. They are sitting inside the pump. They are only condensing the gases. If condensation is not possible, if the boiling point of those gases like helium, etc., are very small, and at that temperature under vacuum, boiling point will further go down. So, if you are cooling a liquid helium cooled cryogenic panel inside a vacuum chamber and you want to pump or condense, it is not possible under vacuum conditions. So, they can absorb these gases. So, at cryo adsorption can enhance the pumping mechanism. We will see all these things little later in detail. So, basically the definition of cryopumping is where the gases are condensed onto the surface or adsorbed onto the surfaces, thereby they are retained on the surface, so that remaining space in the closed chamber will feel vacuum conditions. But this is possible only if you evacuate the entire chamber to at least a thermal vacuum of 10 power minus 3 torr before we operate these cryogenic pumping surfaces, because you cannot establish cryogenic temperatures in various panels inside vacuum unless you produce a thermal vacuum of 10 power minus 3 thermal insulation vacuum. So, we do not require any backing vacuum pumps, continuously backing a cryogenic pump like a diffusion pump, turbo pump, we do not require here, but we require a pre-vacuum pump. It pre-evacuates, keeps it ready, close the valve, isolate that main pump. Now, cryopump will start. Cryopump starts means cool down starts. Cool down a surface, then it will start condensing gases if their boiling points are above the condenser temperature. If they are very nearer, then condensation may not be possible, and also it depends on sticking coefficient of the gases on the surface. We will see all those concepts. So, adsorption and condensation at cryogenic panels which are housed inside a vacuum chamber after pre-evacuating by a process another vacuum pump, which is should be dry, that should not be oily pump, and gets isolated there. This cryogenic pump starts cooling. It will not positively displace the molecules like other pumps. They will straight away convert these gas molecules into liquids, solids. That means, this nitrogen gas I can positively displace by a turbo pump. In cryopump, I will convert this nitrogen into liquid nitrogen or solid nitrogen. It will be a part of the wall or a panel which is maintained at cryogenic temperature. Walls of the vacuum chamber will be room temperature, but inside that vacuum created by pre-evacuation at 10 power minus 3 torr, a cryogenic panels will be there, big panels, cooled by several mechanisms. What are those mechanisms? It can be a refrigerated cooled cryopumps, it can be a liquid cooled cryopumps, or it can be a continuous flow type of cryopump. Means what? Here, this is the most simpler pump. It is nothing but a cryogenic container, liquid helium container, cryogenic temperatures minus 269 degrees centigrade. How to produce cryogenic things, that is in another course, we will see later. Now, this annular space is a vacuum, thermal vacuum for cryogenic temperatures to establish, but you can put a small port here and connect it to any other vacuum system, that will be also evacuated, but you should not start from atmosphere. So, this is called liquid helium pool type cryopump. You can also circulate liquid helium onto a big copper block, an extended surface inside your vacuum chamber through proper insulated lines, and this whole surface will be maintained at cryogenic temperatures with the help of liquid helium circulation pump. This is called continuous flow cryopumps. Both these things are not that convenient. Nowadays, since last 30 years, a new technology called cryo refrigerated technology based on Gifford-McMahon cycle is developed. In fact, the impetus for this technology has come from semiconductor industry. Semiconductor people want clean atmosphere, not only -8, -10, 10 power -8, 10 power -9 tar. We also want very clean conditions, oxygen free, like that. So they have encouraged. In fact, some of the cryogenic companies were supported by semiconducting companies in the initial days. So like that, cryopumps have taken over other pumps as a high quality ultimate pumps. But of course, turbomolecular pumps are also routinely being used in process applications. Okay. Every pump has got its own speciality. We will see the selection criteria of various pumps in various levels in the last lecture of this production schedule, where I will cover selection criteria. So, gases are not positively displaced, they are condensed or adsorbed. Okay. So, ultimate vacuum is very high and the conditions are very low temperatures. And when these gas molecules are touching them, the interactions are van der Waals type of interactions, dispersive forces. Okay. It is not like Gattering, which is a chemical thing, which is there in ion pump, which you have covered in the last class. So, it is basically fundamentally van der Waals dispersive forces on condensers, having some adsorbing materials stuck to that, so that gases coming to that surface either be condensed or adsorbed. A combination of all these processes produce 10 power -10 -11, which is identical to a space vacuum, which is highly required in particle accelerators, which is very important in semiconductor manufacturing. So, how it looks like a typical construction? It contains various sub blocks, a pre-evacuation pump, which I have already explained, with a roughing wall. So, the chamber, which can be a semiconducting process chamber, or it can be a nuclear chamber, or it can be a space simulation chamber, that is roughed by this line and valve is closed. Now, cryopump through this main valve can be opened to this to produce further vacuum from 10 power -3 to 10 power -10. And this cryopump contains an expansion device type thing connected to a compressor. Any refrigeration has got one compressor, one expander type, we call it evaporator type thing. But here isothermal compression followed by adiabatic expansion or isentropic expansion. These two processes are utilized in producing very low temperatures up to 10 Kelvin to act like a condensers or adsorbing agents, thereby producing ultra high vacuum. Okay. And as I already told you, you require a 10 power -3 tar vacuum before we switch on this cryogenic operation. Switching on our cryogenic operation means switch on the compressor and valves are open and closed. There is a cycle called Gifford-McMahon cycle, which is a very popular cycle I have given here. And it is basically isothermal compression and also isentropic expansion, and in between there are regenerative heat exchangers. It is a involved technology. If time permits, later we will cover it. Otherwise, you can contact me, we will be able to give you very good materials on that. So, a typical construction of a cryo-refrigerator pump will look like a small refrigerator basically, and a chamber and a roughing wall and a roughing line and pre-evacuation. But this pump also should be of high quality. You cannot simply produce 10 power -3 tar. This should be dry pump, because if initial vacuum of -3 has got oiliness or something, even final vacuum will have some signature of this oily or water vapor or something, which may not be acceptable in semiconductor industries. So, it is not only important to produce very good quality vacuum, the quantity vacuum, quality is also important. Quality with respect to a particular process. Some processes do not want hydrogen, some processes do not want helium even, some processes do not want oxygen mainly, nitrogen for example, or hydrocarbons, because like typical analytical instruments, they do not want hydrocarbon contamination at 10 power -9 tar. They do not mind 10 power -8 tar with hydrocarbon, because that signal from that will interfere with the other signals from your sample, and your sample chemical composition will be read in a erroneous way. So, that way there are stringent requirements in high-tech areas not only to have 10 power minus 9 minus 10 torr, but also have very clean atmosphere. So, the history of evacuation right from atmosphere is very important. So, the roughing pumps also should be dry pumps. You can use, if it is very large chamber, then you can use claw pump or screw pump. Otherwise, you can use dry membrane pumps or typical scroll pumps, etc., which are coming up recently, last 30-40 years. They are being developed in a very high quality products in various companies. So, the operator of this cryogenic operation to produce high vacuum must be having knowledge of cryogenic side as well as vacuum side. Cryogenic side, cool down of a condenser, and vacuum side, opening all the valves and pre-evacuation, all those things, so that pump down calculations also should be taken into account. And how to make these cryo-refrigerators, all this is an involved technology with interdisciplinary ideas. So, it is very interesting pump. There are quite a good number of books and articles available in internet. You can see that, and in the process you will also start appreciating cryo refrigeration knowledge. Okay. That way you will be benefited in cryopumping study, both high vacuum, ultra high vacuum required for most modern applications as well as cryogenic aspects. Okay. Continuing the operating principle, now inside this cryo refrigerator, I have not shown the compressor side because that is isothermal compression at room temperature. There compression produces heating, we remove the heat of compression. Here we are not bothered more than that. So, high pressure line, low pressure line are bringing them to this expansion device. This particular device is now shown more in detail here. It is a closed device with high pressure helium, which will not condense at those temperatures. So, it is working like a working gas with the valve assembly and connected to HP and LP lines from a compressor. They will produce second stage 10 Kelvin, first stage around 70 to 80 Kelvin. From here you extend a small cup type of structure which will act like a radiation shield to the second stage, and same first stage is also having a connection, mechanical connection to a baffle called chevron baffle, so that from the top the surface of the vacuum chamber to be evacuated, whether it is a semiconductor chamber or anything or space simulation, that room temperature surfaces or hot surfaces should not be exposed to cold. So, radiation, heat radiation should not come here. That is why this 45-degree angle chevron has designed, so that radiation is a straight line phenomena. The radiation will not fall here. The intermediate temperature around 80 Kelvin, by anchoring it to the first stage, will produce like a radiation shield towards the inlet sides. And from the chamber vacuum side, chamber also is kept within the vacuum chamber. No, it is not a positive displacement pump as I told you in the beginning. It is only entrapment pump of the molecules in another phase, liquid phase or solid phase. So, that way these cold conditions are preserved here, and gases can condense here itself. If their boiling points are of that temperature, they need not travel to the second stage, like water vapor and carbon dioxide can be condensed there itself. And if they cannot be condensed like nitrogen, hydrogen, argon and helium type thing, they will start entering into inner stage. From vacuum point of view, this is all integrated up to your chamber. There will be some gate walls in between, I am not showing. So, finally, those molecules which cannot be condensed in the first stage, they will enter into the second stage. Depending on the sticking factor F, there will be pumping speed per unit area. I have given an equation. Of course, I am not going to cover in detail. If you want Wikipedia cryopumping, if you go there, you will get expressions for pumping speed which is proportional to area. By putting charcoal or other things, you are actually enhancing the effective area much larger. That way, condensation probabilities and adsorption probabilities for those gases which cannot be condensed also increases. With all this combination, we will be able to produce a very good surface area using charcoal, activated charcoal at very low temperatures, like 1000 meter squares per gram you can have. That way, increased surface area will have increased condenser area, that way, or adsorbing area. With these things, cryopumping surfaces which should not be exposed to room temperature. So, we have already taken care by the baffles, and this way we can produce low temperatures and very good pumping actions. So, this is a sort of cryogenic pumping fundamentals or operating principles, and the expressions can be derived more in detail following kinetic theory, etc., if you want as an exercise later. Extending these cryopumps to very large chamber, like entire building type of chambers, like I will show you. So, this is the type of cryopump, largest cryopump available. This is the size of the man. So, such cryopumps cooled with liquid helium are available to evacuate big space simulation chambers, where entire space shuttle will be there in the vacuum. I will show you separately. There will be a section on space simulation technology using cryopumps and turbomolecular pumps and various dry pumps, etc. That time we will concentrate on only space simulation using large cryopumps. Right now only technology we are discussing. Okay. When you want such large things, one cryo refrigerator, one baffle, one stage of cryo refrigerator may not be enough. So, you can arrange several cryogenic surfaces. This is a schematic diagram I have given. So, these are arrays of cryo refrigerators. This red color is first stage of cryo refrigerator type. This will be 10 to 20 Kelvin type if it is a refrigerator cooled, or you can also cool it with liquid helium. That way very low temperature 4 to 10 K surfaces are blue, and this red color things are around 80 Kelvin, which are acting like radiation shields from both sides, and the outermost chamber is the vacuum chamber. Okay. So, this sort of very large chambers require several such condensers. Condensers are these blue color things. So, one shield, one condenser and one common backing shield. That type of arrangement is known as cryopumping array, and that will be very large UHV chambers. When you want to evacuate, we have to use them, and this is the most modern technology where lot of manpower is required. That way, whoever wants to read this cryopumping more in detail, I can personally feel as a teacher, you can give startups, you can also get lots of employment potential in nuclear industries, space industries, because they definitely require ultra high vacuum technology and cryogenic engineering. Okay. So, they are fully aware of these technologies. So, if you say that I have mechanical engineering, I have electrical engineering, I know most of the engineering, science, physics, but I can also have skills in vacuum technology and cryogenic technology, then your potential increases. So, cryopumping is large scale arrays is an extremely useful technology for future space missions and nuclear missions, which are very important for any country. Okay. So, this is a type of model I just wanted to give, because nowadays everybody wants to have some modeling. So, you can model these things. These are three is nothing but a series of shields, this series of condensers, this is a back shield, this is a room temperature vacuum shield. That means a small cut view of a one particular place, and one is the radiation, thermal radiation, two is the mass flow, the gas flow, which can bend, that is why I have given wavy nature. So, that how heat transfer point of view you can do some modeling and calculations, and the real mass transfer, I should not say mass transfer in a strict sense, the gas flow into the condensers, that also you can calculate, because the probability, we are already under high vacuum conditions 10 power minus 4. So, molecules when they touch here, mean free path is quite large compared to the gaps here, and gaps have to be created, otherwise heat transfer will be more. So, there is a competition between heat transfer and gas flow. So, there are lots of optimization techniques when you are using very large scale UHV chambers, and even if it comes the other side, that means there is a finite probability for it to come outside, there is a probability that it may not go, it may come back. So, you have to have several probabilities. Finally, solve all those equations simultaneously to produce net amount of gas flow which is irreversibly trapped onto the condensers, so that you will get the ultimate vacuum, required vacuum into the actual application chamber. Okay. So, this is my condenser, and even if molecule comes here, it may stick, it may touch, it may stick, it may not stick. That probability also you should take. And if it misses this gap into these gaps, and it may touch this and again come back here. So many varieties of things you need to paths of these gas molecules. These are not ions. Here we are not bothered about ionizations. Molecules are condensed. Molecules are not positively displaced. These gas molecules have become solid molecules. It is as good like a stainless steel chamber. So, all that, because of lack of time, I will not go into intricate details of this modeling, but this is a very important area, and how do we arrange front end radiation shield, actual condensers, back ends and vacuum chambers. How do you maximize the pumping capacity of the arrays, and very ultra high vacuum conditions exactly relevant to particle accelerators as well as space simulation chambers. This is a very challenging task, I would say. That is why I am covering this cryopumping towards the last, because it is last but not the least, because it contains two important technologies, cryogenic and vacuum technologies. And these are ultimate vacuum pumps. They can produce in principle 10 power minus 11, 10 power minus 12 torque. So, with this idea, when you can add cryogenic conditions to cool various condensers, and that you put some charcoal or some absorbing material, and see to that thermal radiation is not falling onto these cryogenic conditions, then utilize them to suck. I do not say suck because it is a molecular flow, because already pre-evacuation is done by 10 power minus 3 torque by another pump, and this way you will get very good high pumping speed of the order of thousands of liters per second under high vacuum conditions. That is why they are extremely useful in semiconductor industries, liquid crystal displays, storage disks, mass production of glass industries, coatings, and very extra large chambers for space simulation applications and nuclear particle acceleration applications. The advantages are no moving parts like piston or cylinder or anything, and they can be oriented in any direction that way, and they are having 4 key advantages compared to other ultra high vacuum pumps. No risk of oil contamination like diffusion pump. Overall pumping speed is very high, 60,000 liters type thing. Very low running cost once initially purchase a cryo refrigerator and maintain properly with your combined knowledge of cryo refrigerators and vacuum pumps and your design capabilities. Then very high pumping speeds for water vapor and light gases. This is a nuisance in semiconductor industries. You are getting very good vacuum at 10 power minus 7 torque. Entire 10 power minus 7 torque is mostly because of water vapor. Why? Water vapor was condensing, sticking to the surface so much, it is unable to come back easily. It is a polar molecule compared to hydrogen or nitrogen or oxygen. That is why when you look at the residual gas analysis of any pumped surfaces, you will inevitably find it is totally containing moisture. At atmospheric pressure, 70% to 75% is nitrogen, 20% oxygen, third price goes to argon 1%, and depending on the relative humidity, or if you remove with air blast in rotary pump etc., you can reduce water vapor also to 0.1% at higher pressures around 100 millibar or something. But when you come to 10 power minus 9 torque etc., if 10 power minus 9 torque is 100%, you will find 70-80% is water vapor only. Most of the other gases would have been removed over the history of evacuation. So, it has become a nuisance because that is interfering with your semiconductor contamination. So, it has become a big problem. That is why semiconductor industry people, to produce very large VLSS, very large scale integration chip manufacturing people and all, and very high quality chip manufacturers, they have sponsored this cryogenic cryo refrigerator type cryo pumps, and today this coordination has worked very nicely, and that way commercial cryo pumps are available. But there will be some limitations. It requires some basic knowledge of cryogenic engineering. Pumps cannot be continuously running. This is one very important. Unlike positive displacement turbomolecular pumps, because they have come, they have gone. But cryogenic containers, after some time lot of layers are formed, condenser, it gets saturated. Pumping will be difficult. Just like we change charcoal after 4 or 5 months in our water filters at home, because it got saturated, adsorption mechanism. Condensations also, lot of thick layers are formed, then heat transfer will not take properly. Condensation also requires heat removal. On one side there will be lot of heat coming from various sources. If that dominates compared to the cooling, then we will not have pumping action. So, at that time what I should do? Stop it or use another cryopump parallelly and regenerate it. Regenerate means heat it, so that all the solid solidified or condensed things or adsorbed gases will come out. So, regeneration is just to switch off and bring it to room temperature, natural regeneration. If required, you may have to drive water vapor by little lukewarm, warming up with the heating elements. So, that and all you have to do as a routine maintenance. You use for 10 hours, and if it is 10 power minus 8 minus 9 without leakage, then it will be working for 10 hours. If it is a leak or something outgassing, it may work for 4 hours. So, you will have to be ready with other parallel pumps and isolate this pump and start repairing it by, that is called regenerating it. It is nothing but removal of earlier adsorbed condensed gases by heating it up. So, with all these things, it comes like a limitation, but actually it is a basic mechanism of desorption, adsorption, desorption. When you adsorb for vacuum production, it is your duty to desorb it, but during that time the desorbed gases should not be exposed to again vacuum. There should be valving, and it should be related to another route somewhere into some medium vacuum chamber. All that precautions have to be seen. We will see again when we go to the systems design or applications. At that time we will come back to all these components together, how they are arranged, how the various regenerations are going on, scheduling of these pumps in various applications for semiconductor industries, space industries, nuclear industries. We will see all that later. So, with this idea of cryopumping, we have come to the end of the production of vacuum, and last class of production is we will try to cover selection criteria. There is nothing strict rule about it, but I will give out of my experience some tips of selecting pumps. So, I am sure we are slowly cooling down to cryopumping now, and which is the ultimate vacuum pump for ultra high vacuum applications. Thank you very much.